Hello and welcome to another video. In this video, we're going to be working on count the number of infection sequences from the last weekly LeetCode contest. And in this problem, you're given an integer n and a zero-indexed array, and sick, which is sorted in increasing order, and there are n children standing in a queue with positions 0 to n minus 1. Sick contains the position of the sick children, and at any point, a child in the sick array can spread the disease to another child that's not sick, so it can spread the disease to one of its neighbors, and you have to do this one child at a time. And we're asked to return all the possible different ways that people can get sick. So instead of actually looking at the examples provided, we're going to make our own, and we're going to group this into two different categories of examples, and then we're going to combine those together and get an answer. So let's first get one example. So let's say n equals 5, and the sick child is child 0. So all of these other children are not sick. So we'll just write it like this. So our sick array will just be child 0, just like this. And so our children left over that we have to figure out the infectious sequences for are 1, 2, 3, 4. Now the question is, for something like this, what are all the different ways the children can get sick? And this one should be pretty straightforward because essentially, since child 0 is sick, 0 is next to 1. So we can actually draw it, instead of drawing it like this, let's actually draw it in here. There we go. So we have to follow a certain order, right? Where like child 1 has to get sick, and then child 2 has to get sick, and then child 3 has to get sick, and then child 4 has to get sick, right? Because if there's only one sick child, and all of the people that aren't sick, there isn't anything on this side, then there's only one combination possible, and that's just 1, 2, 3, 4, right? So we can write that down. And this is going to relate to, when we have these sick children, this is going to relate to the ends of the array, right? Like when we have the actual ends of the sick children, let's say n is like 100, and the ends of the array are just like 2 and 98 or something. That means all of the children over here and all of the children over here have to get sick, and there's only one possible order for that. So that's the first part of this problem. Now the second part of this problem, let's figure out this kind of same thing, but now let's figure out what happens if instead of only child 0 is sick, let's have 2 children sick. So we will rewrite it. So we'll have child 0 sick, and then child 4 is sick. And now let's figure out like what are all the different combinations here. So notice at every single point, you're going to have a choice of the left or right child getting sick, right? Like if you have to pick one, like child 1 can get sick here or child 3 can get sick. And then once we pick one of those, let's say we pick this one, then child 2 can get sick or child 3 can get sick. Then let's say we pick this one, then for the last child, there's only one. So the number of combinations, we can calculate this out mathematically and just show a couple examples to verify. If we have n numbers, it's going to be 2 to the n minus 1, because for the last child, that's the only one left. So if there is a sick person on both sides, and we can pretty much break our array down into this section or this section, and we'll show how to combine those. So if there is a sick person on both sides, the number of ways here, it's 1, the old one is 1, and here it is 2 to the n minus 1, where n is healthy children. So let's just verify this real quick. So this would be 2 to the 3 minus 1, so it'd be 2 to 2. So we should have 4 combinations. So let's see. So in the beginning, we can either pick 1 or 3. So if we pick 1, then we can pick 2 or 3. So we can have like 1, 2, 3, or we can have 1, 3, 2. Now if we go back, what if we pick 3 first? Then we can pick 1 or 2. So let's say pick 1, then we pick 2. Or we can have 3, and then we can pick 2, and then 1. So these are all the combinations. So that is correct. Let's do one more for one extra number just to verify this completely. So let's say this is 4 now, and we'll have 5 that's sick. So in theory, we should have, in the beginning, we'll have 2 children who are sick, right? Then let's say we pick 1, then we'll have, so let's say we have 2 children who are sick, we'll pick this one. Then we have 2 children who are sick, let's pick this one. Then we have 2 children who are sick, let's pick this one, and then we have this, right? So we have here, it's going to be 2 to the 4 minus 1, so 2 to the cubed, and this should be 8 different combinations. So let's kind of walk through the combinations. So the first child that we can pick is 1. Then the second child we can pick is either, or the first child we can pick is either 1 or 4. We'll start off with 1. So then the second child is either 2 or 4. Let's say we pick 2. Then it's either 3 or 4. So let's say we have this. Then we also have, actually I'm going to write it out without the commas. It's going to be a little bit faster. So we have 1, 2, 3, 4. We also have 1, 2, 4, 3. Now if we go back, so if we do pick the 1, we can also pick 4 second. So then we can pick 4, and then the same thing, we can have 1, 4, 2, 3, 1, 4, 3, 2. And now the first child we can pick, it can also be a 4, right? We can pick 4 because it's right next to a sick child. So we can do 4, and then we have to pick either 1 or 3 after that. So let's pick 1 first. So 1, and then like 2, 3. Then we can also have 4, 1, 3, 2. Then if after 4 we pick 3, then we'll have 4, 3, 1, 2, or 4, 3, 2, 1. So we have 8 total combinations. So that is correct. This is all the ways. So that's the first part of this. Like we can just divide this up. We can divide the sick array up into groups, right? Like let's say we have some sick, let's say n is like 10, and we have, let's say child 3 is sick, child 7 is sick, something like this. Then we could say, okay, well, let's just divide this array up into groups. So the children that are not sick, let's actually draw the sick ones. Let's move this a little. Draw this in blue. So let's say 3 and 7 are sick, which means the ones that aren't are 4, 5, 6. So that's one group. And then 8, 9 are not. That's one group. And then 0, 1, 2 are not. Right? And for each group, what are the number of combinations for the group? So this is going to be the first category where we only have one sick child on the side. So that's just going to be, there's only one way to do this, where it has to be 2, 1, 0 for that group. Then for this group, there are 2 sick children. So this will be the 2 to the n minus 1. And then this is going to be the first category again, where there's only one sick child. So it has to be 8 and then 9. So now that we know for each group how many different ways we can group those numbers in, the problem is we need to add one more variable, and that's what group do we pick from first, right? So let's say we can group this in one way. We can group this in 2 to the squared, so 4 ways. We can group this in one way, but there isn't like 4 ways to get this, because we can pick a child out of any of these groups first and second and third, right? Like we can pick 8 first, or we can pick 2 first, or we can pick 4 or 6. So that adds another level of difficulty. And to explain this, we're going to break it down into another kind of example, and then we're going to apply this to this problem. So let's break it down into a simpler example. Let's say we have a bunch of A's and a bunch of B's, right? So we have A's and B's, and we have some count of them. So let's say we have 4 A's and 2 B's. And essentially we're asked, what are all the different combinations we can make here? And so if you know probability, basically what that works is you have 6 slots, and you can do it either way. But let's say we're going to say 4 is the thing we're placing. Both ways is going to yield the same answer, but let's say 4 is the thing we're placing. So really what we have to figure out is in these 6 available slots, because we have to have 6 letters, what are all the different ways we can place A's? Let's say we place A's like this. This is one of the ways. For whatever way we place A's, the B's have to take up the rest. So we don't have to figure out how many different ways can we place A's and B's. We can just figure out one of them, right? And because all the A's are interchangeable, it doesn't matter like an A and one A is equal to every other A, right? So they're not distinguishable. So the way to do this problem is to do n choose k, which means if you want to place A's, the way it's going to be is the total, which is 6. So that's n, so n equals 6. So 6 factorial. Then it's n minus k factorial, where k is the thing you're placing. So k, in our case, will be a. So we'll have 6 minus 4 factorial. And finally, we also have k factorial, which is 4 factorial. And notice if I was to flip this around, it wouldn't matter, because let's say we're placing the b's, it would still be 6 factorial. Now n minus k would be 6 minus 2, which would be 4. And then we would also have the k factorial, which would be 2, right? So the n minus k part would be 4, and then this part would be 2, so it would get the exact same thing. So this is how to figure out if we have A's and B's, how do we place the A's? This formula here. So now if we go back to our original problem, let's try to apply this. So we already figured out like all the number of ways we can, let's actually delete this part. Yeah, let's delete this part. So we already figured out all the number of different ways we can arrange each combination. So once we factor that in, we can treat every group as the exact same thing because we're already factoring it in, right? We're going to multiply the number of ways we can arrange each one of these by each other, right? So it's going to be like number of ways for group 1 times group 2 and so on, right? For every single group. So now that we factored that in, that we're going to factor that into our output, now essentially every number, you can treat every number in the group as the same. So we can basically rewrite this as A's and B's. So we can have A's, B's, and C's because we already factored in the number of ways we can arrange it. So really what we're asking is for one specific arrangement, how do we place this? So then this can be C's. And now we're basically asking, okay, let's go one at a time. So what we want to do first is let's try to place the B's. We don't need to place the A's because originally for the A's, there's only 3 slots. So there's only one thing you can do. But now we have to go one at a time for the groups. And we basically have to do this n choose k, where k is the thing we are placing. And n is the total slots we have. So here, if we're trying to place B's, we have 3 B's to place. So k is 3. And we already have the A's placed. So n is going to be 6, right? It's going to be the A's and the B's. So n will be 6. So n choose k to place the B's will be 6 factorial over k minus n factorial, which is 3 factorial, and 3 factorial. So that will be how many ways we can place B's. Now we also have to place the C's. So for the C's, how many are we placing? We are placing 2. And n, how many total slots do we have now? We have 8. So n equals 8. And so to place the C's, that's going to be 8 factorial over n minus 2, so 6 factorial, and then 2 factorial. And then for each group that we place, we have to multiply all of these n choose k's, right? So we'll have n choose k for this one times n choose k for this one. And remember, n choose k here is you wouldn't have to do it because basically n choose k here is we're placing 3 things in 3 slots. So it would be like 3, n would be 3, and k would be 3. So we'll just get 1 there. So for this, we don't have to do it because we'll just get 1. Now you could do it as well, right? So just to prove it, so it'd be like 3 factorial over 0 factorial over 3 factorial. 0 factorial is 1. And that's pretty much how you have to do it. So to sum up in all of this, so the entire thing is n choose k for each group multiplied by each other and multiply that by the number of ways we can arrange each group, right? Number of ways we can arrange each group. So now for this, let's walk through our kind of like our solution here, what it would be. And then there's one more part that's kind of tricky as well. So let's just walk through what our solution would be. So the number of ways we can arrange the group, remember, is just this number of ways is just going to be 2 to the n minus 1. So here, this group, remember, because it's on a corner, there's only one way to arrange it. This group, because it's on a corner, there's only one way to arrange it, right? Going back to our, let's see if I have it saved. Yeah, this part right here, right? Because it's on a corner, we have to actually just go this child and then this child, and same thing for this side. We have to do this one, then this one, then this one. So this is 1, this is 1, this is 2 squared, which is 4. So the number of ways we can arrange this group will be 1 times 4 times 1. That part we took care of. Now we just have to do n choose k for all of these. And once we do n choose k for all of these, you're going to see a simplification. That's going to be kind of good. So let's do that. So for n choose k here, remember n is just 3. So it'll be 3 factorial over 0 factorial, 3 factorial. Okay. Now let's do the next group. So here n is 6 and k is 3. So this would be 6 factorial over 3 factorial, 3 factorial. And for the last one, n is 8. And the k is 2. So it'll be 2 factorial 6 factorial. So notice here that when we do this, we have a lot of stuff that cancels out, and this is always going to happen. So if we look here, the n that's used for the previous n choose k is going to be in here as well, right? You can see that. So the n that's used for the previous n choose k is going to be the n minus k for this one. Actually, let me check. Yes, okay. So the n here is the n minus k here. And the same thing here, the n that's here is the n minus k here. Because if you think about it, the total here is going to be some n, and then the k that's used here was the old n, right? The n minus k here was the old n minus whatever we just added. So because this is always going to cancel like this, now let's factor these out, right? So let's factor out this, with this, with this, with this. And now what do we get? So we actually get 8 factorial, and this is always going to happen. So we get 8 factorial, and notice 8 factorial is actually just all of the total number of patients that got sick. And this is always going to happen over, so this 0, 3 part, this 0 factorial doesn't matter, so it's really going to be 3 factorial, 3 factorial, and 2 factorial. So notice that this is the same as n, where n equals, where n is total patients, or total healthy patients that need to get sick. And then the bottom part is factorial of every group multiplied, right? So the first one is a group of 3, and then a group of 3, and then a group of 2. So we have 3, 3, 2. And so we have that. And then remember, we're also multiplying that for every single group. We're also multiplying that by the number of combinations. So we can write that as well. So number of combinations for every group, right? We're going to have the numbers there. We're going to multiply all of those, and we're going to multiply this. So now the tricky part is, and this is actually pretty tricky, is this is going to get really big really fast. Like, we can't just get factorials of huge numbers. And we can't, well, I guess this way we actually can, but like here, let's say, these things are going to get pretty big. So we need to figure out a way to, or actually, sorry, we can't, right? Because like, let's say every single, like, let's say n here is like 10 to the 5th. And then we have like 1 sick patient. So the number of healthy patients is going to be basically 10 to the 5th. And we can't do like 10 to the 5th factorial, right? That's way too big. So we need to figure out a way to take this, and we need to figure out how for factorials to keep the number small enough to where we can actually compute a factorial. And this is where you're going to need to know some modular arithmetic. So first of all, let's go over like how we would calculate a factorial really quickly. So let's say we have like n factorial. So this is basically like the answer, and now we have to mod it by mod. And then the rest part of the problem is just going to be figuring out how to actually keep this number small enough to do this. So if we are trying to calculate a factorial, let's say we're trying to calculate a factorial, that's going to be quite long if we don't cache or do something, right? So n factorial is going to be the same as n times n minus 1 factorial. And we can just pre-compute this for every single number from 1 to n, like where n is like the length of the array. But the problem is, like I said, we can't do like 10 to the 5th factorial. So we need to have some tricks. And so the first trick we're going to use is, or this is the main trick we're going to use, is since we need to mod the entire result by k, what we can actually do is, if you need to mod an entire result by k, like let's say you're trying to do like a times b times c mod k, what you can actually do with modular arithmetic is you can mod each of these numbers, whatever you want, by k first. So this is the same thing as a mod k times b mod k times c mod k. And you don't even have to mod them, right? So these are all optional. So this is the same as just like a times this. Like this is totally fine, where you could just say like, I'll just mod a by k, and then I'll keep the rest. So this is all the same as long as you mod the final result by k. And so what this allows us to do is instead of storing entire factorials, we can store factorials mod k. So we can store n factorial mod k. So we can store, instead of storing n factorial, we'll store n factorial mod k to keep our factorials small. And if we want to get, let's say, n plus 1 factorial, remember that's going to be n times n plus 1, or n minus, it's going to be n plus 1 times n factorial, right? But because we need the whole thing mod k, we can just store n factorial mod k. So we can store n factorial mod k, and then we can multiply that by n plus 1 to get n plus 1 factorial mod k. So we can just do this. So we're going to store n factorial mod k, then we're going to multiply by n plus 1, and then we're going to mod k again. So essentially our recursive function will be something like factorial of x equals factorial of x minus 1 times x mod k. And that's because you can mod by k before or after any multiplication, and you can mod any part of the multiplication by mod k. Like you can distribute it however you want because of this thing right here. The a times b times c mod k is the same thing as a mod k times b mod k times c mod k. So that's what we're gonna use. So we're gonna keep our factorial small this way. That way, we're always gonna keep all our results small. So if we do have to multiply a number by another number, all of our numbers will be less than mod k, or less than k. And so that's how we compute a factorial. We can just keep modding by k, and we can do this. But now the question is, there's this other part that's tricky, and that's we have factorial. We're gonna have like a factorial on the top, but on the bottom, we're going to have all these other factorials, right? And so how do you do like 1 over n factorial mod k? Like, how do you keep this small? And to keep this small, you basically have to use Fermat's theorem. So, and basically what Fermat's theorem says is if you want to calculate the inverse factorial of a number, so if you have n and you have... So if you have n and you have a prime k, then n times n to the k minus 2, this whole thing mod k. So you need a prime k, and you also need n to not be divisible by k, but they give you 10 to the 9 plus 7, which is totally fine, because that's a prime number, and n will always be smaller. So this mod k will give us, I don't know why I kept writing this like mod k, this should just be k, but yeah. This mod k will give us 1. So basically, this is the inverse of n mod k. And because, like I said, with the multiplication property, you can put in this mod k anywhere you want and still multiply it out. So this is the exact same as n mod k, or we can write it like this, n mod k times n to the k minus 2 mod k. Or just like this, right? So this is going to be 1. And so basically, in order to get 1 over n factorial mod k, we can just use that. We can calculate n factorial, and then we can just say, okay, let's take n factorial and power it to the k minus 2. That will give us the inverse factorial. And in Python, there's actually a method to do this. So you could just, it's called power, and you take a base and an exponent, and then you can also give it a mod field, so it'll keep the number small. So it'll keep the number small, and it's pretty easy to, you can write this yourself if you want. Like, if you're in a language that doesn't have this, essentially the way to get a base to an exponent, like if we wanted 2 to the 8th or something, you basically split it up into like 2 to the 4th times 2 to the 4th and so on, and then you have some base case. And the way to keep it small is 2 to the 8th is 2 times 2 to the 7th. So because of this, if you want to get some exponent mod k, you can just say like this is the same as 2 mod k times 2 to the 7th and so on. So you can keep modding like each separate part by k to keep the number small. But in Python, this already exists. So that's pretty much everything we need to actually calculate this and to keep the number small. And if you don't do this, if you don't cache factorials and you don't keep the number small, then you're going to get like some too slow error, basically. So that's kind of the hard part about this problem is not only do we have to figure out this whole combination thing, right? How to get all the combinations for every single group, but also how to actually keep the factorials and the inverse factorials small enough to where this actually passes. And so, yeah, I think that's most of it. So now let's actually just look into the code. And I already have the code done because I don't want this to be like too long of a video. So let's walk through it. So we're going to pre-compute every single factorial from 0 to n. And essentially, like I said, you just take the old factorial, multiply it by whatever number we're on. So factorial of 5 would be factorial of 4 times 5, and then we can mod it by mod. Because using the multiplication property, we can mod by mod anytime we want if we're multiplying numbers. Now the inverse factorial is going to take this power, and it's going to take the factorial of the number. And then remember, for Matt's theorem, it's mod minus 2, because we want this power to the mod, we want this to the mod minus 2 power. Now, funnily enough, you can also just directly calculate the inverse. So you can just do to the -1 power. This will also work. But yeah, if you wanted to write it yourself, I don't think it would be that hard to write the power. Essentially, power works in logarithmic time by dividing the exponent in half. I think there's like other ways to implement it, but that's one of the ways. Then what we need to do is we need to check the edges of our sick people. So we basically need to check the left edge and the right edge, and that's going to be our case where if we go back to the picture, back up here, that's going to be this case here where we need to figure out like how many people are there on the edge, because those people are going to have, there's only going to be one way to sort those people. So we're going to have those two groups first, and then we're going to look at the rest of it. So we get the group on the left, we get the group on the right, and then finally, we need to go through the array and we need to look for gaps between sick people. And the gap between sick people is going to be case number 2, where you have 2 sick people, and then you have a gap in between there, right? So you can have something like this. And let's say you can have like 1 and then some healthy people over here, and then you'll have another like sick person, and then some healthy people over here, and then another sick person, and so on. So each of these gaps is what we need. We need to figure out just the length of it. We don't really care about the index for the permutations. So we get all the gaps, and then our groups will have all the groups of sick people, with the first 2 groups being the ends. So the ends can be 0 as well, but 0 factorials once, that's totally fine. So now what we need to do, remember, is our formula, if we go over here, is, where is it? Here it is. So it's the n factorial, where n is the total number of people. And then we need to multiply it by the factorial for every group, which is these inverse factorials, or we need to divide it by a factorial for every group. And then we also need to get the number of combinations for every group. So that's basically what we're doing here. First, we get the factorial of the entire number of healthy people. Then we go through each group, and we first need to figure out the n choose k, or not the n choose k, the inverse factorial for each of these groups. So we'll just take our old result and multiply it by the inverse factorial for each of these groups. And then also for the groups, other than the first 2, remember the first 2 groups, the only way they can be sorted, right? Like the only way they can be arranged is only one way. So here there's only one combination for, let me see. Yeah, for this, it has to be in this order. But for the rest of the groups, it's in this order. So then that's what we're doing. We're essentially saying, let's skip the first 2 groups because we don't need to get permutations for those. Like those have to, the permutations for those is 1, but then let's get the permutations for all of the rest. So it's just going to be 2 to the power of n minus 1, and then mod. So you basically do that, and then you return the result. So it's like a bunch of parts together, and then you have to keep these small enough, and you also have to either pre-compute your factorials or cache your factorials to be fast enough, because if you don't cache factorials, like let's say you try to get, 10 to the 5th factorial, and then you try to get it again and again and again, it's going to be very long, right? So we just pre-compute every factorial, and that'll be n time. And then we can submit this. So this is kind of a lot, and you do have to know, like, this is good. I think this is a good problem for learning combinatorics, but then the problem is you also have to know, like, a bunch of these other things, like inverse factorials, how to keep factorials small with mods, modular arithmetic, which is not super common problem. So if you aren't doing like competitive programming, hopefully this is helpful to get into it. But yeah, I don't really see how you would do it unless you're like a math major or something, because it's kind of hard to do it without knowing these things. So yeah, as you can see, it's kind of slow. I did notice there were solutions that ran this in like 200 ms, which is really weird, and they were basically the same kind of logic. So I don't really get. I think that's like a LeetCode thing where they use like a cache or something as well, and for some reason, yeah, I don't know. There must be some weird like caching thing or something, because I looked at the code and it was like basically the same logic. Like there wasn't anything tricky. So if anyone knows like why the couple solutions that are like really fast, what the changes, you can let me know there. So let's go through the time and space for this one though. So to compute every single factorial, because we're keeping these small, that's going to be O of n. And then to get an inverse factorial, technically, to get a number to a power that's really big like this to a really big number is going to be a logarithmic function. But I think most people just treat this as O of 1 because, like I said, to the power you're basically going bit by bit. This power might be a little bit optimized, but I think realistically it's logarithmic. But people just say it's O of 1, so we'll just call it O of 1. So essentially, we are going through every single one of our people, so that's O of n. And then for every single one of our people, we are just adding into the group. And then once we go through the group, this is all just, well, let's call it linear time. You know, you might argue n log n, like I said, because this power is technically, I believe, logarithmic. Yeah, so to add people to the group is O of n, and then to go through the groups is also O of n. So it's just O of n total. And for the space, let's see what we have here. So to compute the factorials is O of n. Well, or you could cache. Either way, it's going to be O of n. Inverse factorial, we're not caching. Groups is also O of n because technically you can have like n groups. And yeah, I think that's all of it. So kind of a lengthy one. Hopefully this was helpful. Yeah, kind of a lot. So let me know if it was helpful or if you have any more questions. It did take me a while to solve. And like I said, you do need to know modular arithmetic. And I think the combinatorics part, you actually, like I did see that in other problems before where you're trying to put like one group into another group. That part I would take out of it. Modular arithmetic kind of rare. I think the main thing, just remember that, yeah, if you do have like that A times B times C mod K, you can actually distribute out the mod anywhere you want before doing those operations to keep the number small. That is kind of useful. So yeah, in either case, that's going to be all for this one. So hopefully you liked it. And if you did, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.